here is a result which is even more remarkable than that one. OK, because one thing that it's tempting to think at this point is that all infinite sets are of the same size. So like if sets so different as the rational numbers and the natural numbers turn out to be the same size, you think, well, like once we move to infinity, like basically any infinity is the size of any other infinity. But it turns out that that is not correct. OK, so the next thing we're going to prove is that there are more real numbers than natural numbers. And because the natural numbers and the rational numbers are in fact of the same size, it follows from that result that there are also more real numbers than rational numbers. There's so many real numbers that I actually don't even need to look at all of them. So all I'm going to do is I'm going to look at the real numbers in that interval. So the real numbers bigger or equal to 0, but smaller or equal to 1. And what I'm going to show is that even in that small interval, there are more points than there are natural numbers. And the way I'm going to do it is I'm going to proceed by reductio. So I'm going to assume the opposite of what I want to prove. And I'm going to show that you can prove a contradiction from that assumption. So if that assumption leads to a contradiction, it can't be right. So the opposite of what I want to prove can't be right. So what I want to prove has got to be correct. So this is what I'm going to assume for reductio. I'm going to assume that there is a 1-1 function from the real numbers in 0, 1 into the natural numbers. So notice, if that were true, then we would know that the cardinality of that guy is smaller or equal to the cardinality of the natural numbers. But we also, we trivially know this. We know trivially that the cardinality of the natural numbers is smaller or equal to the cardinality of these guys. So can anyone think of a quick proof of this? So in other words, a 1-1 function that takes us from each natural number to a number in there?
Just the function 1 over that natural number?
Correct. So I'll do that over here. So function that assigns, well, it's not going to work for 0, but I'll correct that later. So it assigns to 1, 1 over 1, and assigns to 2, 1 over 2, and to 3, 1 over 3. And of course, all of these guys live comfortably in there. And what about 0? Well, we can just assign it whatever other element of there we want, provided it wasn't already taken. So for example, pi minus 3. So that means that we know for sure that the natural numbers are equal to or less than the real numbers in there. So if we could show this, that would mean that there are exactly as many real numbers in that interval as natural numbers. What I'm going to do is I'm just going to assume this to see what happens. I'm going to derive a contradiction from the assumption. And if I'm able to derive a contradiction, the assumption can't have been correct. So this must have been false. We're assuming that there is a 1-1 function from the real numbers into n. So let's just write out what the beginning of that function looks like. So what it means is that a bunch of natural numbers got assigned real numbers. So maybe 0 got assigned that one, 2 got assigned 1 got assigned that one. Maybe 2 didn't get assigned anyone. That's fine. 3 got assigned that guy, and so forth. So we have a long list. And crucially, our list leaves no real number out. So every real number in our interval is in this list at some point. So that's what we're assuming. What we're assuming is that we can, in effect, list the real numbers in 0, 1. OK, and now we're going to prove our contradiction. So the first observation en route to our contradiction is that the real numbers in 0, 1 can all be written out using decimal expansion. So we can write each of them out as something of the form 0.A1, A2, A3, blah, 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 where each of these is just a digit between 0 and 9. So I'm going to do it for each of them. So we have our list, and everyone in the interval is somewhere on that list. So now consider the diagonal number. So take the first digit from the first member in our list, and the second digit from the next member on our list, and the third digit from the next member on our list, and a fourth digit in the next member of the list, and so forth. And look at that real number. So we have our diagonal number. That's 0.A1, B2, C3, D4, E5, and so forth. That's just a real number in the interval. And it has an evil twin. So to construct the evil twin, use the following recipe. Where D has a 2, write, for example, 7. And where D has no 2, write 2. That's how you construct the evil twin. So suppose, for example, that our D is this number. Then D's evil twin is going to be 0 point, and then we found something which is not a 2, so we write a 2, and then something is not a 2, so we write a 2, and then we find a 2, so we write a 7. And then something is not a 2, so we write a 2, and then 7, 2, 2, 7, 7, 2, and we keep going. And now we're done. Because D's evil twin cannot be on our list. Why is it not on the list? Well, look, it can't be the first member on the list because this number differs from the first number on the list in at least its first digit. And it can't be the second member of the list because this number differs from the second member of the list in at least its second digit, and so forth. So here's what we've done. We found a number, and this number has got to be in the interval 0, 1, which is not on our list. But we had assumed that every real number in the interval was on our list. So we've proved, contrary to our assumption, that that cannot be correct. So we've proved a contradiction. So if our assumption for reductio entails a contradiction, our assumption for reductio cannot be correct. So we have shown that the real numbers in 0, 1 are not smaller in number than the natural numbers.